So let's write the program. We'll write a program for factorial, and so how is factorial defined? There are two ways of defining factorial. One way of defining factorial is factorial n is equal to 1 times 2 times ... n. This ... business is not a well-defined thing, na? So yeah, it should be. So a proper way to do it is factorial n is equal to n times factorial n minus 1. But of course, this is not again well defined. There is a problem here. There is no base case. So we say an alternate way to do it is f of n, where f is factorial function. So this is equal to 1 if n is equal to 0. If n is equal to 0, then f of n or fact n is equal to 1. Otherwise, it is n times f of n minus 1. I don't want to use this star because we are giving a mathematical definition. This is the case if n is greater than or equal to 1. Did you study these recursive functions in your discrete math course? Yes, no. Okay, it's fine. So now we want to write code. Oh, ECE doesn't have discrete structures. Okay, don't worry, it doesn't matter. Now you know it, recursive function. So we would like to write code to compute the factorial of a number. Okay. So as usual, so we read the input in a variable n and we store the output in variable fact underscore n and int main and then so we say printf enter n /n, no, not /n here, and then scanf %d and then. So finally, after doing some computation, we want to say factorial n equal to %d in fact underscore n. So we have to do some so we need to write a program to compute the factorial of n, and we will write two ways. One way of writing factorial is this approach. We will use a loop. So how do we write a loop to compute the factorial of a number? Should we use a while loop, for loop, which is more convenient? So shall we use a for loop? So, and we would like to store the result in fact n. Our initial estimate of fact n is equal to 1. And for I is equal to 1, I less than or equal to n plus I, We will just say fact underscore n is equal to fact underscore n times does this code work? We have to return fact underscore. It doesn't work, huh? Now also it doesn't work. I have to call the function. Okay. Fact underscore n is equal to loop underscore fact n. All right. So let's compile this program and see if it works. gcc fact.c dot a dot out. See, it works except for /n the beautification factorial 1 great. So factorial, if I give -1, what happens? If it is -1, so if you give -1, -10, so you get 1. You don't get garbage, Nikita. What happens? We don't enter the loop on line number 5. On line number 7 of loop underscore fact n, you don't enter the loop. So you return 1. Okay, that's what happens. If you did not initialize fact underscore n to 1, it would be garbage. Yeah, what you return, it would be garbage. For 0 also, it's the same actually. Yeah. We don't enter the loop for 0 also. So now we would like to write a recursive version of this. Why don't we need a pointer in this case? Why do we use ampersand then? We just need the value of n, right? So you're not going to change any memory location. We just return the value. It is like this. So who asked this question? Appar asked this question. Yes, why not pointers? Appar, let's say you are a factorial function. I tell you, hey, can you give me the value of factorial 4? I tell 4 as parameter. You compute, you tell me 24 as factorial 4 is 24. Do I need to tell me, my address? I mean, from where I am sending my 4 and all. I could be in Hyderabad, I could be in US or in Australia. I just tell 4, you don't need my address to compute factorial 4 and tell me what its value is. So that's why you don't need a pointer. Why do you don't need my address, unnecessary information. Understood all of you who but on the contrary, if you're not happy with me and if you want to punch me, then you need to know my address. Okay. Then I will send a pointer. bad C programming professor, you want to punch me, and then no, then you need my address. But otherwise, I'll just tell that 4, and you get back to me with factorial 4. So that's all. No need for pointer. Okay. All right. So now let's get back here. So we would like to write a recursive version for factorial program. Yeah, so yes, so recursive version, it's recursion follows very close to mathematically what you are trying to do. So what happens? Yeah, so let's do this. If again int fact underscore n is equal to 1, and the question is oh, okay, Pradham's you want to send good wishes to your address, huh? Okay, thank you, Pradham. Okay, so if fact underscore n base case, sorry, if n is equal to 0, then what do? We return 1, and else fact underscore, sorry, actually let's do it this way. Fact underscore n is equal to 1. Otherwise is equal to n times Gaurav has an interesting, yeah, so this is called recursive function. We can call a function, the same function from within the function, and we will take a very detailed look at what is happening under the hood here. But if you think mathematically, does this make sense? Yes, Gaurav, I'll answer your question. In very detail, I'll answer your question. Mathematically, does this make sense? That let's try to compile this program and let's see. Okay, let's compile this program and see if it is working. GCC fact.c 0, 2, 3, it's all working. So now if I give a negative number, what happens? -1. What will happen if I give a negative number? Loop will be good. What happened to the recursive function? So we get into trouble. Will we ever get into statement 19? statement 19, statement on line number 19, we never get there. So we keep on recursing forever, and we will get a segmentation fault. Okay, we get a segmentation fault. So why do we get a segmentation fault? Now let's understand this whole story now. Okay, so now we will do a careful GDB of this program. GDB. Good. So Aman is in understood how things work. Screw up things and do GDB. That's the essence of story. Okay, so yeah, so break main and break recursive factn UI enable. So now the first question for you is we didn't yet run the program, start running the program. The question for you is the, what do I say, activation record for the function main allocated? Is the activation, this is the memory, this is the current state, this is the place where code is present. The activation record for main is not yet allocated because we didn't yet start running the program. So now the activation record for main is allocated. Okay, now you can see when you do BT, you can see the activation record for main is allocated. And if you look at the activation record for main, so let me redraw this picture so that BT shows the program stack. That's true. And drawing is bad, but I hope you get the picture. Okay, so now if you see the program, this is called as program stack or call stack. So we are in main, so main's activation record is present here. And on the activation record for main, memory for variable n and fact underscore n, shall I use fn as a shorthand for fact underscore n? Can you keep in your mind that I'm using fn as a shorthand, not function? Fn is fact underscore n. I'll just write it here. Otherwise, no, it's a pain to. Fn fact underscore n. This is then convention we use. Okay, so now yeah, next, and then I'm entering 4. Yeah, I'll enter 3. Maybe I'll use 4. So now what happens is on the activation record associated with n, you will have n is equal to 4, and fact underscore n, that is fn, is some garbage value. Now line number 35, we just, the loop got executed, and then, so now we are in recursive function. So main may call the recursive factn function. And if you look at the stack trace, you will see that main called the recursive function with n is equal to 4 as parameter. So now what happens is the activation record. So this is, let me use this. The activation record for, let's call it as recursive factorial with 4 as parameter. So this is main called recursive factorial with 4 as parameter. And what will be the value of n here? What is the value of n here in the recursive, in the activation record associated with 4? What is the parameter value n? Annotations are not visible. Huh? Why is it? I understood the problem. How about now? All good, right? Okay, okay. Thank you, thank you. So what will be the recursive RF4? What will be the parameter value n? It will be 4, right? And fact underscore n, after executing line number 16, fn is equal to 1 after executing. Now now we are on line number 18. After line number 18, where do we go? To line number 22. On line number 22, now check, remember, this is how the stack is looking like, call stack is looking like. We are looking at 3 pictures. I want you to pay attention to the 3 pictures that we are doing. This is picture 1, this is picture 2, this is the call stack picture, BT. Using BT, we are looking at the 3rd view. We are looking at the same stuff in 3 different ways. So now we go to line number 22. Next, we go to now, we make a recursive function call to RF4 makes a call to RF3. RF4 makes a call to RF3. So now the activation record for RF3 will be created here. So n is equal to 3. And similarly, Fn will also be appropriately initialized. We will see what happens. Okay. Now, if you see backtrace, you can see main called RF4, RF4 called RF3. And so what we have is RF3. Do you see that the memory for the local variable and parameter n and fact n for RF4 and RF3, they are independent of each other. They don't interfere with each other. There are 2 different activations of the same function, and the memory for the 2 different activations is separate. Are you all with me here? Most important observation. If you understood this observation, then you are good. Awesome. Fantastic. And if you look at the activation record for RF4 remains. Yeah, that's true. On the top of that, RF3 comes. And if you do the backtrace also, and BT also is, see what happens is in RF4 on line number, if you look at here, we are here. So what we are trying to do is here, we are saying 4 times. When we are in RF4, this is, we are saying 4 times RF3. Once you return the value from RF3, you substitute, let's say RF3 returns 6. Then what we get is 4 times 6 is 24, and that 24 gets returned. Again, are you with me here? When in RF4, let's say in a particular instantiation of RF4, RF4 is calling RF3 and RF3 magically gives you the answer 6 and 4 times 6 is 24 and this value you will return at the end. Are you all with me on this discussion so far? Happy? You are getting me? Okay, good. Let's get back. Don't worry about global variables and all right now. Okay, follow the line of thinking I am providing you. Now in RF3, what happens? So now we are in RF3. So we go to line number 22. Now we are in RF3, guys. Okay. If you see backtrace, you will see that we are in RF3. So we are in RF3. And what is the value of n here when we are in RF3? 3 times. And what are we going to do? We are going to call RF2. We are going to call RF2. And RF2 may return some value. Let's say it returns 2. 3 times 2 is 6 and that 6 will be returned back. So if you see, this is the activation record for the RF2. N is equal to 2 and Fn is equal to whatever that comes, we will see RF2. How is Fn1 in RF3? Because on line number 16, we are initializing it to 1. On line number 1, we are initializing it. Okay. So now, yeah, now we are in RF2. RF3 made a call to RF2. Yeah, so already made a call to RF2 and the activation record is still we have already set it up, anticipating that. Okay. Now after line number 16 gets executed, what will this be equal to? Fn is equal to 1. Please follow the trace and then you will understand. And then what will RF2 will do? RF2, so we are in RF2 on line number 22. This is 2 times RF1. Yes or no? 2 times RF1. So call RF1 and this is the activation record for RF1 and N is equal to 1 and no. So and once we enter, let's continue. So what happens is, yeah, so now we are, where are we? If you look at BT, okay, so now we are in RF1. What happens? So where do we go? What's the next line we are going to execute? Next line is, so RF1 calls, no, if N is equal to 0, we go to 22 because N is equal to 1 right now. We call RF0, that is the base case. Yes or no? We will call RF0, no? Not. So this is RF0 and then again in RF0. So we have N is equal to 0 and Fn is equal to something, we will see. So next. Now you can see the backtrace. Are you able to see here? Main calls. I want to highlight this thing for you. This is main. This is main. And then with RF4. This is 3, so on and so forth. This correlation I want to see. So finally, so here you can see RF0 is here, and so these two pictures are equivalent to each other. All these three pictures, they are equivalent to each other. Are you fine with this? The equivalence of these three pictures? The rightmost one, back trace, and the middle one. All these three are equivalent to each other. So now we are in RF0. What happens when we are in RF0? Which line we go to? We go to line number 18. From line number 18, we go to line number 19. So what does RF0 returns to RF1? I will use a different color. RF0 returns 1. And what will RF1? So when RF0 returns, what happens is the activation record associated with RF0 gets popped out. Let's see. Let's see. So now, next, you come out, and if you see BT, yeah, it's still not yet out. So now if you see BT, the activation record associated with the RF0, it got popped out. Okay, it got popped out or deleted. So this will go. Does this make sense for you? That when we return from RF0, the activation record associated with RF0, it is deleted. Are you fine with that statement? Yes or no? And from RF1, what will RF1 do? RF1 returns, what does RF1 will return? RF1 returns 1 times 1 to RF2, and RF2 returns 2 times 1, and RF3 returns 3 times 2. Did I get it right? Or and RF4 returns 4 times 6. Do you see how? And every time we go back, the associated activation record gets wiped out from the, gets deleted from the stack. This is called as program stack or call stack. Can we consider it similar when we return from a function? This is how exactly, whether recursion or not, this is how exactly it happens. Recursion or not, recursion takes more. Excellent point, Rohan. Rohan made a fantastic point. In the loop, the space required is constant, but whereas here the space required is proportional to n. So in this case, for factorial, this is recursion is a more expensive solution when compared in terms of space when compared to loop. I will come to that point later. Very nice point. Okay. But do you conceptually, are you with me on this one? How the activation records don't interfere with each other? Okay. There are different versions or activations of the same function. They don't interfere with each other. And as we keep coming out, the activation records keep popping out. So this is the first idea. If you're all happy with this, the next important idea is the idea pointed out by who pointed out? I forgot, Rohit or someone, that the recursive version here is more expensive than the loop version, because we are in terms of space. The depth of the stack is Rohan. So very good point, Rohan. The depth of the stack is proportional to n. Whereas in the loop, the memory that we use is constant. The memory that we use is constant for the loop case. Very good point. But you know, the memory that is used because of recursion, it is not, you are not able to see it, but it happens implicitly. Okay, so that is the second point. And but sometimes it is good to write recursive functions, not for factorial, but there are cases where the memory required by the loop or the recursive version will be the same. Now, what I meant to say is in the factorial function, the memory, it is better to go with a loop. It is better to go with a loop. But there are other programs where the memory requirement will, whether you write a loop or a recursive function, it will be the same. There it is better, perhaps better to write a recursive function because it's easier for you to think. Fibonacci sequence, I think you think about it, you do the same argument and see how it pans out. Aman, good question. But what I want to tell you is for recursion, there is some cost you will pay, but let's not worry about that cost. But there are some problems where it is easy to solve the problem if you think about the problem recursively. Otherwise, it will be hard for you. No, it's a very good question, Sarthak. Any program that you can solve by recursion, you can solve by loop and vice versa. But there are some problems where recursion is very handy. It's very easy to write the program. Can you give some examples of such programs? Maybe in 1 week, 10 days, I will try to give. Yeah, quick many sorting algorithms, Aman rightly pointed out. Good, Aman. So like, for example, when we try to do quick sort, thinking recursively is helpful. Med sort also, thinking recursively is helpful. And n-queen's problem, yeah. So that's a very nice problem where recursion really helps. And for determinant also, you know, try to solve the problem for the determinant of a matrix. If you should try to see if recursion is comes in handy for you. So yeah, so now that you learned about recursion, go try to solve the determinant problem today using recursion. If you solve the challenge problem, you know, today, tomorrow, you'll be on a high for the midterm exam. Be determined to solve the determinant problem. See, I want to tell you one thing. I think, no, you guys refuse to. See, what happens is, if you see main, in this program, before we called the recursive function, we called the loop underscore fact. So if you look at the kind of the memory, before RF4 got called, loop underscore, this memory space is used by loop underscore fact10 function. When you call RF4, that same function, that same space is used by loop underscore fact10, and this is not necessarily overwritten. Are you with me here? On line number 35, main is calling loop underscore fact. So before RF4 is called, loop underscore fact10 is called. So the memory for loop underscore fact10 is also the same. It kind of overlaps for the memory. The memory that is allocated for loop underscore fact10, the activation record, it gets deallocated and it is reused for RF4. So sometimes when you go look at the values, you know, like for example, if you read the value of n or fn before you do anything, you may get some stale values from loop n can sneak in there. Stale values can from here can sneak in there. It is possible. Are you with me here? Does it make sense? That Sarthak is continuously asking the same question, so I thought I'll. No, it is Shauno fact underscore n is written even in RF1 also, no? You compute. Before I answer Shauno's question, are you with me on this loop underscore, the reuse of space between RF4 and loop underscore fact10? Does it make sense? Because it's like someone vacated the home and, you know, and says new person entered. The person who vacated the home, he vacated not by wiping off everything, he just vacated. No, it's like, what is the stale value? You are in your hostel room, you vacated and you didn't take all your stuff there from your room. Someone else occupied the room, so they get all your stale stuff. That's all. The memory, this chunk of memory, previously it is occupied by loop underscore fact10. When loop underscore fact10 is out, the same memory locations, the same slate. It's like in a board, you know, like you enter a classroom. In the previous lecture, if something is written on the board, then the same stuff, if the faculty didn't wipe off that board, then you will see the same values written on the board. Yes or no? Exactly the same. There's no difference, except that here the board is some transistors. Voice gone, huh? Do you understand analogy? So you think of board, these are transistors. Okay, that's all. Memory of RF3 is related to RF4. No way, the RF3 and RF4 memory, they are not, they are separate from each other, right? This and this, they don't interfere with each other. This and this, they don't interfere with each other. This and this, they don't interfere with each other. And other thing is, in the case of RF0, the value that flows, this value flows here for RF0. For anything, for RF2 or whatever it is, the value that flows here is this. Does this make sense? That RF0 fact underscore 1 on line number 19, it goes to 25. In all other cases, RF1, RF2, RF3, the value on line number 22 gets flowed to 25. Are you all with me on this one, the last point, this flow? This is important. This is the base case. This is the base case of the recursion. If you don't hit the base case, you are in trouble. And one more thing, why there is the system crashes. If you give a negative number, what happens is the stack keeps on growing. Okay, so let's say, for example, main calls RF minus 1, and RF minus 1 calls RF minus 2, and RF minus 2 calls RF minus 3, and RF minus 3 calls RF minus 4. So the activation records, it keeps on growing, and finally they hit the code segment which is read-only, and because of that, you don't have permission to write on the read-only segment, and you get a segmentation fault. Seg fault. So there are lots of questions on the chat box. I want you to think about those questions, because the questions that you have asked, the answer to all the questions is there on the screen. Are you with me so far in the discussion? I know some 2-3 students, you are flooding the mailbox with same questions again and again, but I want to know, generally want to get a feel. Okay. Sorry, I want to understand, the main important ideas, whether you got it or not. So that's the reason. Yeah. So now, kind of, so this whole picture, the picture is staring at you. Did you get the segmentation fault thing? Why we can get a segmentation fault when there is an infinite recursion? So you keep on growing, the stack keeps on growing, you go and hit the code section, and at the code section, it is read only, you cannot write it. When you try to overwrite it, the operating system kills the process, is saying you don't have permission, and raises a seg fault. Yeah, on line 18, we can fix this problem by saying if n less than or equal to 0. That's the way to fix it. But I wanted to use this to illustrate this point that we can get, if the base case is not done properly, then we can get a segmentation fault. Now I have a question for you. When we are in RF1, is it possible to access RF2, RF3, RF4's data? Yes or no? It is possible if we have the address of them. It is possible if we have the address of these variables, then it is possible to access. Like, for example, let's run this program again. Okay. Okay, now see, yeah. So where are we in now? In the GDB, where are we in now? Are we in RF2 or not? Or are we in RF1? We are in RF1, right? Yes or no? We are in RF1, right? Because you can see on line GDB BT says, here, if you notice this, we are in RF1. So if we are in RF1, then I use this command up. When we do this command up, we are telling GDB to go here to RF2. So let's do, we are in print n is equal to print n is equal to 1. When we do up, what happens is we are in RF2, and if I do print n, we get n is equal to 2. Yes or no? Are you with me now? We did one up, and we are kind of retaining the activation record stack as it is, and we are playing with it cleverly. Do you see what we are trying to do? When you say up, you go one level up. And if you do one more level up, what do you get? If you go one more level up, I will do one more up. And then if I do print n, it is 3. If I do print fact underscore n, what will it be? Fact underscore n. We initialize it to 1, it will be 1. So we did one more up here. I want to point this to you. Now we want to come down. Now if you do next, then the stack will be reset. You'll come back to RF1 and you continue working. Now let's do one more down. When we do down, we come down. So are you down? BT print n. We are in RF2 because we did a down, and then again we do a down. We do print n. We are in RF1. This is the original state of the system. Do you see what is happening here? Are you able to see how you can use GDB to go up and down the stack and observe what is happening? And why do you need this thing? Is when you get a bug in a problem, what happens is in practice, when you are working with a complex system, due to a bug, your system crashes. Then if your system crashes, then what is the state of your program which causes this crash is a very, very important thing to know. You will be able to almost instantaneously go and say, hey, this is the cause of the problem. You would look at the stack trace, main called RF4 and RF4 called something else, something else, something else. There is a crash and you just look at the stack trace and the stack trace will tell you, hey, this is the problem that caused it. Are you all excited to see this fun? See, VS Code also has internal GDB, but this gives you the GDB native interface is extremely powerful. Super powerful when compared to the VS Code. VS Code internal GDB is like, yeah, it's good, but this is more. I agree with Vinkesh and Vansh. Yeah. Okay, and also it helps you to show off your skills. Okay, guys, I think no, that's true, Abhinav. So I am just kidding. So even VS Code uses GDB in the backend, I understand. And it's good to use VS Code and see how these things change. But knowing both is good. No disagreement with Abhinav there. Shall we stop today's class? Are you all happy, excited? You're all hungry? Okay. Okay then. So we'll stop